So, welcome back. We stopped with the skewness thing. Okay, great. So there are easy adjustments for the gauge which have been entertained in the literature to keep capture skewness. Now, I think it's very instructive to look at that. That would be a gauge 1-1. So you have the gauge component. Wait, my chat is off. We don't see the screen. Thanks for mentioning it. Thanks. Yeah. Okay, great. Okay, so that's a gauge 1-1. So we have the variance for t-1 to t depends on the lagged variance. It depends on the most current return innovation. And then you see there's an indicator function. So if the most current return innovation is negative, you are, assuming θ1 is positive, you are increasing the loading on the return innovation. So we know from the data, if return shocks are negative, variance tends to shoot up. There's a negative correlation between volatility and returns. It's called leverage effect. In case you want to Google that. And you capture that here. That's how you build a model, yeah, kind of. You build that in mechanically, not mechanically, it still needs to be estimated, but within the likelihood procedure, conditional on parameters and on your model, you always know what the epsilon t sequence looks like because you observe the returns. You condition on parameters if you optimize. So conditional on a parameter draw, you have a sequence of epsilons, and then you just check if the epsilon in t-1 was negative, the loading is alpha1 plus theta. If not, it's just alpha1. And that's how you get skewness into returns. Why into returns? Because for a negative return realization, the variance gets larger and it tends to give you more probability mass on the left tail of returns than on the right tail. And there's another approach, the exponential gauge, here 1-1, where you model the log variance to be a function of the lagged log variance. And you got some G function here, and the G is also fully parameterized. And there you also see you work with indicator functions. The fundamental eta shock, that's the epsilon divided by your sigma square. That is negative. You adjust the parameters like that. If it's positive, you adjust it like that. And then there is a closed form solution for that expression. I don't have it here in the notes. I think it's in the video. We don't need that. But that is known in closed form analytically. And that the etas you can infer within the optimization from your realized returns divided by the sigma. Just make sure. Here. Yeah, if you observe the epsilons, conditional on a parameter draw in the model, you observe that. You divide by the variance equation, square root of that, and then you also get eta shocks. Okay, so you see how you can build in, that's how you can build in skewness. Gauge is a well-developed mechanics machinery. There are thousands of packages out there. No one estimates a gauge himself, apart we in the past. We always said that. And we will also do it in this course because that is how you get experience for maximum likelihood in financial data science problems with such a gauge parameterization. Okay, it's complex enough so that we have to use a computer, but it's not too complex so that we can still extract intuition from it. Okay, so that would be the stopping point. Oh wait, my chat is gone. It's here. Okay. That would be my stopping point for today. Let's just see what we didn't cover is stochastic volatility model. That's all right. That's the option part. Okay, we need to be fresh. We covered enough, so I give you a nice problem set for free, meaning it's not graded. It will be volatility equals squared returns. You will do that for our return panel. And you will ask the question, I mean, I will formulate that, but just to give you the highlight, you will ask the question, is there a factor structure in cross-sectional volatility? And you will also ask, you will explicitly look at the volatility implication of a Volkswagen. Okay. The way we move, how can we submit the solution of the assignment in order to get it checked? Right. We are still working on this checker. We anticipate it's running by Wednesday. Yeah, I hoped it was running by last Friday, but it took us longer. And then we set it up, and then you can check the solution. Yeah, we are working on it. Okay. No, there will not be graded assignments. Just a final exam. Okay, so next time we talk about the SVM. It helps if you go through the videos of SVM. Yeah, okay. Then I go about the Corsi a little bit, and then we would do the option. Okay, that might take, like I hoped we just use half a class today, but you see it took us more than a full class. Again, I wanted to be too slow, but not too fast. It was important to me today for today. Okay. What we should do, I mean, it's 11:15, so if you have to run, you just run. You haven't looked at the problem set 2 for today. Why don't we just quickly do it for the next 15 minutes? Voluntary problem set allows you to play around with concepts. Okay, so there was this helper function. Okay. Like in the past, we had these graded problem sets, but I wanted to get rid of that to make the course less demanding. So therefore, you just pick up what you want to pick up, basically. The exam is like a minimum requirement later on. Which means you can take out of the course more than what the exam is going to test. So here's like a gentle way for you how you can get yourself into object-oriented programming if you haven't done so. I just programmed a class single index model. And what does it do? Yeah, it just copies in the input, a return panel. I need the factor. And then it's going to compute GLS regressions. So it's going to regress all of the returns. Onto okay, it calls a function linrec_fit. Okay, what that is now linrec.fit. That's the linrec package. I see. So what do I do? Where do the factor is the input, but still factor is the input. It's now part of the object here. And then, oh, that's what I was looking for. And then, that's for the object-oriented self.f1 in the constructor. F1 is assigned to be a member of the class. So now I assign the single factor to be my x. I add a constant like we did it in class. And now I'm just regressing for all stocks. I regress the y, which is the return, also with the self. notation, because in the constructor, I copy the return into the self. And then I just run these regressions. I compute the epsilon. I compute the correlation by the Spearman method. I get the p-value of the Spearman rank test. And I compute alpha and the t-value of the alpha, the beta and the t-value of the beta. Okay. Okay. So what do I do here now? So I'm just reading in this helper function, specify the index model. Okay, I just read in the returns. I specify my factor to be the market return. Okay, it's like the excess return, assuming the risk-free rate is 0. Yeah, so I want to mimic this CAPM idea, market return minus risk-free rate. And then I initialize my class. I run these linear regressions. So that's the nice thing. This class, I program this like my own fitting package now. The class is called sim, single index model underscore CAPM. That always tells me then it's a linear model with one factor. And the CAPM tells me I use the market return as my factor. So now I fit the regression. So I fit the CAPM basically. And these are the adjusted R squares. Yeah, you see some firms have a 65 R square. Others like Volkswagen only have 20% R square. So here the displayed R square values coincide with the relative amount of systematic risk that your Stoxx 50 stocks contain. For example, 0.31 for ADS DE means that 31% of ADS DE, so Adidas, 31% of the Adidas return variance is systematic. Of return, I shouldn't call it variance, I should call it return variations. Variations. Yeah, that's really variations in RT. Okay. Yeah. So it's not the gauge variance or something like that. It's really these epsilon innovations are these art or the RT movements. 31% is systematic, 70% is idiosyncratic, could be diversified. Defend the argument that 80% variance in Volkswagen is diversified away. Well, if you look here, 20% of Volkswagen's return variations is systematic. The other 80% would be idiosyncratic, Volkswagen specific. And that gets diversified away if you put that into the into a well-diversified portfolio. So these are the correlations. Just sim cap row. I had a function. No, I didn't have a function row. I simply had row was a private member. I don't know, private or public. It's, in Python, it's just everything is public. So it's just a member of class. And the row gets computed here. These are the correlations. But these are correlations of firm-specific innovations. That's important. So it's the correlation of the epsilons. Yeah, because if I want to test whether or not I got a single factor model well specified, I need to check whether the correlations in the residuals are 0. Because the single index model says that all the correlation between two stocks comes from common exposure to the market factor, but not through the epsilon. And if just visual inspection, you see, I mean, these variances, they are kind of low. That's 13, 15, it's not low anymore, but it's still, we're not in the area of 80 or something like that. So they are already rather low, but here's 28% between Bayer and BASF. You see, That's a German thing, most likely. Bayer. No. Bayer and BASF. These are even technology-wise related. You see already the CAPM market factor is not a perfect single index model. There is some industry-specific information which it doesn't capture, which is out there. Okay. But overall, they kind of look low. So I just display for every firm the average correlation with the other constituents, display the results as a histogram to get a visual inspection of the magnitude of average correlation. So, oh, I didn't plot that, okay. But on average, the correlations, they are rather low. No, they're rather low. Low, for me, the cutoff point is something like 10%, 0.1. So that is on average, it's low. And the challenge question here, because challenge, we didn't explicitly talk about that in class, is the single index model well specified? I highlighted the videos. In the video, it just tells you need to check whether the residuals are firm specific. So here, my observation is any single stock residual has a mean correlation that is close to 0. That's a good thing for a single index model. Looking at individual correlations show that most correlations are in absolute terms lower than 15%. That speaks for rather close to 0 correlations, which is also a good thing for the single index model. Yet, a few share correlations of 30%, like we had with BASF and Bayer. That is a bad thing for the single index model because it shouldn't. And so the open question is, can we reject that the correlation is 0? And we want the correlation between these two residuals. Yeah, this is Volkswagen versus BASF, or Daimler versus Adidas. Okay, and we would reject that hypothesis if the p-value is small. Yeah, so what we would like to have are large p-values for such a hypothesis test. And if we can compute the p-values of, let's see what we do with Pandas data frame. We take in the data, sim cap m row p-value, and we just give the Pandas frame an index. So it's computed in our class. And that is, again, computed here. I just use a Python package for the Spearman correlation. It gives out the p-value. Now, I cannot, at least I didn't find that I can test for the entire correlation matrix here. I need to test firm by firm. By basically checking whether, I have to go firm by firm. I have to check Adidas. Is Adidas epsilon p correlation of 0, correlation 0 with the other firms? How about Daimler, and so on and so forth? So basically specify the single index model for every firm individually. Okay. And here I'm just plotting basically these p-values. And I know I would like to have large p-values in order to have a well-specified single index model. I got 42 firms, and I see the mean correlation, but that's the p. The mean p is 0.1. The median, but the median is much smaller. So it's skewed to the right. So I basically see also when I look at the 75th percentile that most firms have a small p-value, meaning statistically speaking, correlations are not 0 among residuals, right? This says what I saw here, these correlations here, I said they are below 0.2. It's my rule of thumb from an economic point of view, but from a statistical point of view, the cutoff point is somewhere else, and this road Spearman test, it just tests for it, but tells me that the p-values are very, very small. So wait a minute, what does it mean? Looking at the quantile, most share small p-value. Right, therefore I have to reject that these autocorrelations are 0. And that tells me it's not a perfectly, in a statistical sense, not a perfectly specified index model, single index model. So I should keep adding indices. But I also know that these other indices, when I look in terms of the principal components, they don't add much in terms of variance. The second PC did add 5% variance, the next 3%. So I already get the feeling I would have to add lots of additional principal components in order for the linear vector model to have zero autocorrelation and zero correlations in residuals. Therefore, my next thinking was, let's think about from an economic point of view, how big are these correlations? Because here we just know they are not 0. But are they now 80% or are they 20% or are they 10%, right? That makes a difference from an economic point of view. So here I'm just plotting the rows, the correlations, the describe function. So I see for Adidas, the correlations are rather low, for the others as well. So kind of my takeaways, economically speaking, most correlations, if I look at the 75th, 25th percentile, are in the range of -10 to 10, which I think, economically speaking, is rather low. So therefore, can we do better? As I said, if we add more factors, eventually the epsilon has a correlation of 0 among each other running these tests. But I wouldn't do it because the PCs don't add much in terms of variance explained. And economically speaking, the epsilon's correlations are rather small. Therefore, from a practical point of view, I would consider the single index model with 1 over n as my portfolio, as my index, to be a valid vector model. Not perfect, but valid. And if anything, that's my personal thing, most people left already, but if anything, my reading of the data, what we've done so far, is, let's summarize. One factor drives 45% of the variance. A second factor in terms of PC return seems not useful. But I see that the epsilons still co-move, like BASF versus Bayer. That was a nice example. They have a 30 correlation. Now, I think what one should do is to use time varying factor loadings, make the beta time varying. And that would solve the problem with BASF and Bayer in my ex ante thinking, because Bayer and BASF, they are kind of in the same industry, like chemicals, and they have a similar beta. And therefore, if I make the beta time varying, the epsilon will be more IID than it's right now. And it makes sense that the beta is just time varying. And we could do that, right? We could just make a beta be time varying. And then we have a quadratic single index model. We have a single index, which is random. It's a random variable, but the beta will also be random. And that's why the entire model would be a quadratic model. And we could use the expectation maximization algorithm to filter out the beta. Therefore, we will learn expectation maximization in the vol section. Maybe if you remind me, if I remind myself, we can make an application as a problem set where you filter out the beta about what I just talked here. And then I just have 2 links. Agree. What's that? I don't know. Okay, it's a bit small. Cap M and expected time, the cross section of expected returns, right? It's just to show that this time varying beta idea is not something crazy. The failure of the static cap M to explain the cross section of returns is well documented. We also saw that, right? Even for US data. So thanks for the problem sets that you did as a group. For US data, the CAPM also has a negative slope. In this paper, we show that the model's performance dramatically improves when betas are allowed to be time-varying functions of lag business cycle variables. We use an approach to construct a stochastic discount factor. Interesting, we talk about that also next class. Using the excess return on the market portfolio as the single factor, that's like our CAPM, scaled by a time-varying coefficient, that's the beta. The result is a model in which the conditional factor premium is a nonlinear function of the business cycle variables. Because the business cycle variables will move into the beta, and the beta is time varying. Okay, right. So my thinking, my reading, consistent with that, I can show other sources. I kind of make the beta time varying, and maybe that's the very last thing for today. Journal of Empirical Finance, also an older paper, CAPM over the long run. What do these guys find? A conditional one-factor model can account for the spread in the average return sorted by the. In contrast, earlier studies document strong evidence of a book-to-market effect. However, the betas vary over time. Right. We show that our CAPM with time-varying betas do better jobs. Okay. And right. So, okay, that is. Now, where am I right now? No, I'm kind of. Okay, so therefore, let's wrap up. We started in the vol section. Arch-Gauge. You can look at the videos for that. If you need some further, but the videos just contain what I said, but maybe you have then more time. I will hand out one problem set. It will use PC analysis, single index model for squared returns as a proxy for variance. So you can test yourself for the exam by relying on what we've done in the past with PCA analysis and squared and vector model, and apply to squared returns. I will already maybe phrase the problem set. You will see. Yeah, maybe it's so moving more towards what it will be like in the exam. Meaning, I don't put in equations, but I just put in words, and then you have to translate it yourself into the equation. But we've done it several times, and now you will also practice. Great. And then next week, we do the stochastic vol model. We will use a package, which means we still don't do the hard coding ourselves. I still want to do package for Gauge, package for that. Maybe I even give you a problem set for Gauge, then we can move a bit faster, and I give you the package for Gauge already. And then I do in class the SVM. That would be next class. I talk about options, and then the second next class, we would start to do the coding ourselves. Might be, I have to think about it. Or maybe we move into options first. You can give me your preference later on. Because these are two big learning points, the option as well as expectation maximization to do it hands-on ourselves. Okay, many thanks. I took a bit longer today. I apologize.